So question 3 is on alpha amino acids, and serine is an alpha amino acid because you've got a carbon atom that's attached to an NH2 and a COO, a carboxylic acid group. That is the alpha carbon. So if you react serine with sodium carbonate, it's going to react with the acid bit of the molecule, and you're going to form the sodium salt. Reaction 2, you've got the acid, and you know that acid and alcohol, carboxylic acid and alcohol makes an ester. You need a bit of acid to make it work, also reflux. So the OH in the acid goes, you make a new bond to the O in the alcohol, and the O in the alcohol, because the H goes to make water, is attached to a CH2, and then you have this benzene ring. Right, now that was 1 mark each. Third mark was a little tricky. Now because you're using an acid and you've got an amine group at the end of the reaction and the leftover acid is going to protonate the NH2. So if you remember, if you put it down as NH3 plus, that would have given you the third and final mark. But just 2 marks in total if you wrote it down as NH2. Right, and esters of course are used because they are sweet smelling, so in perfumes, I could have said fragrances, and also as food flavourings. Get any one of those 3 for 1 mark here. Next they give you a synthetic route to make serine. Got a few different transformations, and on the next page they refer back to this series of reactions. The first thing they want is the reagent and so the chemicals you use and the conditions for reaction 3. So go back to reaction 3. Right, and the difference there is you go from a haloalkane to an amine and make amines from haloalkane by using ammonia and ethanol as solvents. Right, next, what sort of reaction is occurring in reaction 4 and reaction 5? Reaction 4, what's changed? Well, you go from a primary alcohol to a carboxylic acid. That's an oxidation reaction. Oxidize an alcohol to a carboxylic acid. And then in reaction 5, what's changed? Well, this bit of the molecule has changed, and well, if I draw this out fully, a COOC, what you've got there is an ester. Okay, so CH3, and you go back down to an alcohol. Right, so what you've done there is break the ester bond. Okay, well, you've got the O left, and the way you break an ester bond is by hydrolyzing an ester. Okay, then you go back down to the alcohol and the acid. So what they don't show you over here, once you hydrolyze it, of course, you're also going to make ethanoic acid, this bit here. So oxidation and hydrolysis. Even I'm putting down a nucleophilic substitution reaction, that's sort of going back to AS chemistry, F322. Okay, but we'll stick with hydrolysis, that's the recent example you've come across at A2 chemistry. Okay, tricky question over here. So you've got compound E, you've got the formula for it, molecular formula. It's one of 2 optical isomers. You know, you've got 1 carbon with 4 different groups attached to it. Here was the giveaway. It can be oxidized by using Tollens reagent, and only aldehydes can be oxidized by using Tollens. So for compound E, part of the molecule must be a aldehyde. Okay, C to a bond OH. Now, it's oxidized to, there's only one thing you can make, a carboxylic acid. So F must be a carboxylic acid, but it also says that it's a amino acid. So if I oxidize it to the carboxylic acid, the only way I can make it into an amino acid is that carbon. You must have a carbon that's attached to both the COO and the same carbon, a NH2. That's what an amino acid is. Okay, so once again, compound E is an aldehyde because It's oxidized by tolerance. Only aldehydes can oxidize by tolerance to a carboxylic acid, and that's F. F is also an amino acid. That must mean in this carbon atom, we've got a Cu, you also must have an NH2. Right, then you fill the rest of the molecule. Compound A, so that means compound A must also have had the CNH2 there as well. And now let's look at the formula. You've got 4 carbons, so let's try 2 in a straight chain. Right, 1N, which you've got, 1O, which you've got, 7 H's. Right, 1, 2, 3, 4, 5. Now that would give you 6, 7, 8, 9 H's, but you only want 7. Right, so you could have from 9 H's to 7 H's. You lose 2 H's by making an alkene. Okay. You know the alkenes over here because, well, it could not have gone there. This carbon would then have had too many bonds. Well, first of all, it would not have been a chiral carbon. It says it's got 2 optical isomers, so you need that carbon with 4 different groups attached to it. Got 1, 2, 3 groups. That must be the 4th group. You then put a double bond there. That carbon would have too many bonds. It would have 5 bonds. You also could not have put the double bond there. Once again, that carbon would have had too many bonds, 5 bonds. Another thing you could have done to lose 2 H's is make a ring. And again, if you try making a ring, for example, a triangle by losing 2 H's, you would have found once again that carbon would not have 4 different groups. It's got 2 optical isomers. That means it has a chiral carbon. And this carbon here is chiral. You've got 4 different groups, 1 a H, 1 a Cu, so 1 an aldehyde, 1 an NH2 and 1 an alkene. Right, so we figured out what compound E was. That fits the formula C4H7NO. Right, and then we can now figure out what compound F was. It just been oxidized from the aldehyde to the carboxylic acid for the rest of the molecule. Careful with this carbon, only 1 H because that gives it 4 bonds, another H down here would have given it 5 bonds. Now that was just 2 marks out of the 6 that were going. Right, next it says the alpha amino acid F forms 2 different polymers G and H. Now that makes sense, okay, because if the alkene, if that bit there polymerized, you'd form a addition polymer, and if you had the carboxylic acid group reacting with a neighbouring NH2, you make a condensation polymer. Right, and one of those polymers is G, one is H. Well, first of all, let's try the addition polymer. So just remove the alkene bond, go down to a single bond. These are my 2 H's, and I've got a CH, then of course that's the rest of the polymer, and that CH I've also got another CH, and that CH I've also got an NH2, and also on that CH I've got a Cu group. Okay, so that's my condensation polymer, so that's my addition polymer. Of course you can put square brackets around it if you wanted to, but you don't really have to. Right, and next, if I made a condensation polymer, so the Cu would have reacted with the NH2 from a neighbouring molecule to make an amide bond. Okay, I'm just going to draw out the molecule again. So I had an alkene and another CH, CH. Right, careful with this bit. Right, C double bond O. Now the OH goes when you make an amide bond. Okay, that's just the rest of the polymer, and also a H from the N goes. So you're down now to an NH. Again, that there's the rest of the polymer. Okay, so I could even have drawn it this way if I wanted to. And there's my 2 bonds going on to give the rest of the polymer. Right, so I've drawn one repeat unit for each of the, now that one there's a condensation polymer. Right, now which one is G and which one is H? G has the empirical formula C4H7NO2, and the addition polymer is the one that has got 2 oxygens, 1 N, 7 H's and 4 carbons. Okay, so the addition polymer must be compound G, because the second polymer H has only got 1 oxygen. This one here has only got 1 oxygen. If you count the rest of the atoms, you should find it also fits that formula. Okay, so there's 1 mark for each of the repeat units, and another mark each for saying that you had the addition polymer and a condensation polymer. Sticking with polymers, here's a repeat unit of polyglutamic acid. How was it polymerized? You want to draw the structure of glutamic acid, so that's probably going to be a carboxylic acid. Right, so what you've got here is, well, initially that would have been an OH, so we'd had a carboxylic acid, and that would have been an NH2, and of course those two ends are of what's reacted and been polymerized. Okay, so let's reattach the OH and the H that initially left to make water when we made the polymerization reaction to make the amide bonds. So you go back to carboxylic acid on one end, NH2 on the other end. Note that you have an amino acid here because you've got a carbon attached to both an NH2 and a Cu. That's what you need for a alpha amino acid. Right, that was 1 mark for the monomer. As we've seen up here, it can be polymerized. Now, it then says you had a student who tried to make the polymer. Now, they've not made the polymer, however, so no polymer was found in the mixture, so you made something else as a mixture, so perhaps 2 or 3 compounds or more. And this person has then isolated 2 of the major compounds that were made. Again, it's not the polymer, it's something else. And the hint they give you is you've got the mass spectra of these compounds. Right, molecular ion peaks, so they've got a mass of 129 and 258. The first place I will start is by figuring out what the mass of the monomer was. Okay, and then you can try to figure out what was then made. And if you work out the mass of glutamic acid, it's 147. Right, now one thing you made had a mass of 129, and the difference between 147 and 129 is minus 18. And what weighs 18? Water. Okay, so water was removed, potentially. How could that take place? Okay, a molecule, well, the NH2 and the Cu could, well, it can't be the Cu on a neighbouring molecule, because that will then give you a dimer, or perhaps in a polymer. Right, so it must be the same molecule but minus the water. So what must have happened was the NH2 has reacted with the Cu on the opposite end. You made a ring, so you made a new bond between the N and that carbon. Okay, in a ring, and the ring must have had 1, 2, 3, 4, 5 atoms, so a 5-membered ring. Right, I'm just going to start off by drawing a 5-membered ring. Okay, and just start filling it in. Right, so let's say that carbon, well, let's say the N was over here. Okay, and then the N was attached to a CH. Okay, so it's a CH, and the CH was also attached to a Cu. And then continued being attached to a CH2, another CH2, and then of course you had the carboxylic acid. Of course the OH has gone, you form a new bond to the N, and N has now gone down to a NH. The OH from the acid and the 1H from the NH2 have gone to make water, so that was your compound that you made. Okay, which was a little tricky to draw out. Right, and that's got a mass of 129. Right, second thing that you made has got a mass of 258. Let's try 147 times 2. That does not give you 258. It gives you 294. Okay, so we've got 147 times 2. And the difference between 258 and 294 is take away 36. Okay, so you've lost something with a mass of 36. Okay, so once again, 258, so 147 times 2 does not give you 258, it gives you 294. And the difference between 294 and what you actually made, 258, is 36. Well, once again, 18 goes into 36 twice. Therefore, potentially 2 waters removed. Right, so potentially 2 amide bonds being made. How could that happen? Well, here's glutamic acid once again, the same molecule drawn out down here. Now, what if 2 of these molecules combined, drawn a second neighbouring molecule? Okay, so we've got CH, Q, NH2, and then the rest of the molecules CH2, CH2, Right, so potentially what could have happened is the NH2 and this carboxylic acid reacts to make an amide bond. Once again, that one also reacts with this NH2 to make an amide bond. Okay, so 2 amide bonds releasing 2 molecules of water. That makes sense. Again, it was pretty tricky to draw out, however. But what it would then make is a 1, 2, 3, 4, 5, 6 membered ring. 1, 2, 3, 4, 5, 6, yeah. Okay, now again, this was tricky to draw out, so let's have the CH at the top. That's 6 membered ring. Let's say that's this CH, and it's bonded to an NH. Going to go down to an NH because one H is lost to make the amide bond, and then in that same ring, so I'm going to draw a hexagon. I've got the C double bond O. It's now attached to this nitrogen, NH, which is attached to that CH, which is then attached to the CO. The CO has formed an amide bond with that NH2. And then you had to fill in the rest of the molecules. Also on that CH, you had the CH2, 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 CH2. Same on this CH, CH2, CH2. So CH2, CH2. Now that was very, very tricky. Yeah, just 1 mark each here. Surprisingly so. Right, continuing with polymers, part D. You have to work out the functional groups in polymer J. That probably helps if you draw out the displayed, or at least the functional groups. You've got a CO, C double bond O, and then you've got CH2 4 times. It's in a straight chain. It's an alkane. And you've got another CO, NH, that's going to be an amide bond. So that's one thing you got, an amide. I could even said peptide. Right, keep going. CONH, amide bonds, attached to a C, and you've got next 2 CH3s as branches, and CH2. Oh, right, okay. Here's a tricky bit. So they might have said a ketone or perhaps an alcohol, which is not an alcohol. Right, it's a polymer. So the this O is attached to a C double bond O over here. Okay, so in other words, this repeats itself over here. Right, and you've got CO single bond attached to a C double bond O. That is a ester. Okay, so you've got an amide and also a ester group in that polymer. If you were to draw out, let's say for example, 2 repeat units or a few more repeat units. That was tricky to see. Right, next you have 2 different monomers that react to make polymer J. Well, it looks like there was an OH there from a carboxylic acid, which left to make water. And then you can break that bond there, so that was also a carboxylic acid. And this must have been a next monomer. Now to make the ester bonds, that must be an OH from an alcohol, also an NH2. So I'm just going to put in the OH for the acid. You had CH2, 4 of those in a line. And lastly, I made a mistake. Yeah, so it says display the functional group, so I'd actually put in the OH bond there. Right, that's one monomer. Next you had an NH2, again display the functional groups. A C with 2 CH3 branches. CH2, and finally a OH. That was one mark each there. Right, then once you've made the polymer, it says the polymer can be washed away easily with water. Why? So two possible answers. Either it might have been a case that the polymer can form hydrogen bonds with water, it had to say with water, or alternative possible answer, because you've got ester groups in your polymer and amide functional groups, well, they can react with the water, they can be hydrolyzed, so the ester bond and the amide bonds can be hydrolyzed. So just one of those answers for 1 mark there.